Section 15.9. Multiplication modulo p. When the multiplication is done modulo 2 to the power n, the low-order bytes are weakly enciphered, and we need to jump through hoops to fix that weakness. This problem does not occur when the multiplication is done modulo a prime, p. With a large multiplier, each bit of the product depends on every bit of the plaintext. There is a different problem. Let's assume you have chosen a prime p less than 2 to the power n and a multiplier m with 1 less than m less than p. This lets you safely multiply the values from 0 through p minus 1 by m modulo p, so Riva can decipher these values by multiplying by m prime, the multiplicative inverse of m. However, the plaintext value 0 would be left unchanged, and the plaintext values from p through 2 to the power n minus 1 cannot be multiplied safely because the result would be ambiguous. For example, 3 and p plus 3 would give the same result when multiplied by m modulo p, since 3m is congruent with pm plus 3m mod p. So Riva could not tell whether the message was 3 or p plus 3. This means that values from p through 2 to the power n minus 1 would have to be left unchanged. To do this, define the function mod p as follows. One solution for this problem is for Sandra to exclusive OR a secret value to the plaintext. This suggests a family of modulo p ciphers. Let's settle on the values n equals 64, meaning a block size of 8 bytes. The prime modulus p equals 2 to the power 64 minus 59, which equals 18446744073709551557, and the multiplier m equals 39958679596607489, which is also prime. Sandra enciphers a 64-bit plaintext block B by choosing a secret 64-bit constant C1 as the key and computing x equals mod p brackets C1 exclusive OR B plus C1. This is the first cipher in the family. Call it p mod 1. It is rated 5. The second cipher in the family, p mod 2, is 2 iterations of p mod 1, using a second 64-bit constant C2. p mod 2 is rated 7. The third cipher in the family, p mod 3, has 3 iterations and is rated 9. The fourth member, p mod 4, is rated 10. It has a total key size of 256 bits, 4 times the block size. Each of the additions is done modulo 2 to the power n, not modulo p. The 4 p mod x ciphers are all extremely fast because 64-bit addition, multiplication and modulo division are all directly supported by most programming languages. In some computers, they are a single machine instruction. This lets the p mod x ciphers operate on 4 or 8 bytes as a unit, instead of handling each 4-bit chunk separately, as DES does. This class of ciphers is ideally suited for software encryption. p mod 2 is more secure than DES because of the much larger key size, and p mod 4 is more secure than 3 DES. There is a second approach to multiplication modulo p that eliminates the unchanged values. The idea is to divide the range of integers from 0 to 2 to the power 64 minus 1 into 2 separate ranges with a different prime modulus and a different multiplier for each range. Choose 2 primes p and q such that p plus q equals 2 to the power 64 plus 2. There are about 10 to the power 16 such pairs, so they are easy to find. For example, p equals 9228410438352162389 and q equals 9218333635357389229, and 2 large multipliers m less than p and n less than q. The tricky part is that you have to shift each range so that you are only multiplying the numbers in the range 1 to p-1 or 1 to q-1. You do this by redefining the mod p function. With this redefined mod p function, the p mod 1 through p mod 4 ciphers work the same as before and have the same ratings. This diagram shows how the range 0 to 2 to the power 64 minus 1 is divided. Section 15.10. Change of base. Changing the number base is closely related to multiplication by a large integer. Changing number bases is a slow operation when the number is very large, so the best strategy is to divide the message into blocks and convert each block separately. Changing the base blurs the separation between message bytes. There are two methods for converting numbers from one base to another. You can work from the low-order end or from the high-order end. Many people learn these techniques at school, but often forget them over time. To refresh everyone's memories, both methods are illustrated here. We will convert the number 1A87 from base 11 to base 7 using the low-end technique, and then back to base 11 using the high-end method. With the low-end technique, you repeatedly divide the number by the new base. Each remainder becomes the next digit of the converted number. Here are the steps to convert 1A87. 1A87 over 7 is 312 with remainder 4. 312 over 7 is 49 with remainder 5. 49 over 7 is 7 with remainder 4. 7 over 7 is 1 with remainder 0. So 1A87 in base 11 becomes 10454 in base 7. With the high-end technique, you repeatedly multiply the high-end digits by the old base and add the next digit. Here are the steps to convert 10454. 1 times 7 plus 0 is 7. 7 times 7 plus 4 is 49. 49 times 7 plus 5 is 312. 312 times 7 plus 4 is 1A87. If those numbers don't look quite right to you, remember that the numbers 7, 49, 312 and 1A87 are all in base 11. There are lots of neat ciphers you can make based on changing bases. For example, a 16-byte block is also a 16-digit number expressed in base 256. Convert that number to another base, say 263. Now you can transpose the base 263 digits, or perform a substitution, or both. Then you could convert that to base 277 and do the same thing. Finally, you convert back to base 256. This requires a 17-byte number to hold the result. You can use any number base from 256 through 362. Remember that if any result has a leading digit 0, that digit is required so that Riva can decipher the ciphertext. If each successive base is a little larger than the previous, the same number of digits are required at each stage. The number of digits will increase only at the last step, when the number is converted back to base 256. There is no reason that the bases need to be prime. Here is a concept for a block cipher based on base changes. Begin with a secret, well-mixed, keyed simple substitution S. S operates on bytes, that is, on integers from 0 to 255. S can be extended to bases larger than 256 by leaving any digit greater than 255 unchanged. This eliminates the need to have a separate substitution table for every possible base. Choose 3 number bases, B1, B2 and B3, satisfying 256 is less than B1, is less than B2, is less than B3, is less than 363. You will also need 3 keyed transpositions, T1, T2 and T3 on 16 elements. The elements are integers that can be as large as B3-1, so they will need more than 1 byte each. Block cipher 3-base consists of the following steps. 1. Substitute S. 2. Convert to base B1. 3. Substitute S. 4. Transpose T1. 5. Convert to base B2. 6. Substitute S. 7. Transpose T2. 8. Convert to base B3. 9. Substitute S. 10. Transpose T3. 11. Convert to base 256. 12. Substitute S. The cipher block consists of 16 elements up through step 11. Step 12 expands the block to 17 bytes. Cipher 3-base is rated 10.